So my Twitter handle is Jim_Gough. That's purely because that Twitter handle, there wasn't Jim_Gough available at the time. But also I've now heard that underscore is no longer an allowed variable name in Java. So I think we'll keep the _. So a little bit about me before we get started. I'm a university graduate from Warwick. And I was really interested in compilers and performance, and that was kind of it. That was where it ended. And then I started going to the London Java community. And I did a variety of different things in the LJC. One of those was help to design and test JSR 310, which was the datetime library. And I was also a developer and a trainer for a couple of years. And whilst I was doing that, I met someone called Ben Evans, and some of you may have been in his session earlier on today. And we wrote this book together called Optimizing Java. So through the connections of the LJC, we kind of went back and, yeah, wrote something that was really an interest of mine. And it was a really cool book to work on. My day job, I work on API gateways and do things with API platforms at Morgan Stanley. And I'm also an occasional Maven hacker as well. So if you see various banter around Maven and Gradle on Twitter, that's why. So what about this talk? There's actually been some excellent talks about Graal VM and how it works for natively creating images and compiling images and getting really good startup times. I'm going to try and take it from a slightly different perspective. So we're going to try and look at this from the existing JVM that we use today and that we know about today. And we're going to look at the different pieces that are involved in the story of executing Java and where Graal and ahead-of-time compilation comes in to start to complement that. So this is the area that we spend most of our time, writing Java source code. Not many people use Java-C anymore. It's hidden away behind all the build tools that we use, but fundamentally, you're creating a class file. So let's use a really simple example, and this is what's going to kind of run through the talk. We're going to use a very noisy hello world. Okay, so there's not too much Java code to understand in here, and I think the point that was made earlier in the containers talk, it doesn't necessarily have to be Java to benefit from a lot of the performance benefits at the VM level that we will talk about. So I have a public static void main, which says printint, and it does that 1,000,000 times. And in printin, I print out to error, hello world, and number. Okay, so there's a couple of things in there. Some people who've played around with this kind of thing before will be able to spot why I'm doing that. But I will kind of get into the reason for that being so verbose as we go through. So you take your Java source code, you run Java-C, and you get a class file. Now you can inspect what the contents of the class file using Java-P. Now we're not going to go into that in too much detail in this talk. There's some good sort of things on bytecode, and if you were in Ben's talk earlier, you may have had enough bytecode for one day. We'll see. So inside Hello World, you can see the first thing that's happened is Java-C has effectively added a default constructor. So the default constructor running an invoke special on the object in it. So that's something that Java-C has added for you into your class. The next thing is the main, and there's lots of different bytecode examples here where we've got load the integer, store it, do a compare against 1,000,000. If it's less than 1,000,000, carry on going, and invoke static. And yeah, we still have gotos. So all that time when we thought we got rid of gotos, they're still there. The point of this slide is to really kind of show you that Java-C as a tool, it doesn't do very much, right? It just takes your code and converts it to bytecode. There's not a lot of magic compilation that's going on behind the scenes like there would be if you ran something like GCC. We will look at the printint method because this is kind of curious. And this is something that Ben also pointed out. This is a disadvantage of going last. All the things that you want to point out, some people might have shown you already. So we get hold of the print stream, and we do an invoke dynamic on something called make concat with constants. So that's going on behind the scenes, and then we invoke the virtual function and print line to print out the new variable. So that's kind of curious because if we were to take that away and look at the same example in Java 8, you'd actually see different bytecode being created for the same example. So if you're actually looking into the bytecode for Java 8, you'll see we're creating a new string builder. We're then loading in the hello world, and we're invoking the add effectively on string builder. So this is kind of weird. Like, how many people in here have done the kind of like the plus operator inside a for loop, and the first thing you've seen in a code review is, oh, you should replace that with a string builder because string builders are better there because they're better performance, and they'll kind of, you'll only create one object and you won't have lots of strings floating around. Well, that's kind of weird now because that just doesn't hold true at all. And where you potentially would get better performance from like 8, 9 plus, you kind of maybe have limited yourself. So there isn't much that goes on in Java-C, but as the platform evolves, there's different things that will actually appear here. So we've got our class file, so everything that happens outside the JVM. We now want to effectively get it into our environment. So we use something called the class loader. Okay, so this is the bit we'll talk about next. The class loader plays an important part in our story because it's generally not known what's going to happen when the JVM starts up. Okay, so in Java, classes are loaded just before they're needed. And you've probably seen this when you've seen a class not found exception, no class defined error, or maybe you don't see that because your build tool is amazing and it hides that away from you. I see a lot of laughs. No, we still see that. You still see that coming out. So what happens is that class file, it gets mapped into a class object with a K. And this is the C++ representation. And the instance methods are held in the class vtable. And then you get static variables that are initialized once and held in the instance class with a K again. So that's kind of an interesting representation. The main thing that we're doing here then is taking what was in effectively your class file and mapping it into what is effectively like a cache of your methods and your static data that you'll then run in interpreted mode. Now, one way I want to try and show you that class loading is a little bit magical is actually by writing a custom class loader. So this is something that you can do. There's various different implementations that people have of this. And hopefully, this will all work fine, live demos and all. So this is something I've got on GitHub. Happy to use it or play around with it if you like. It does a couple of things. It does a couple of weird things, actually. This is deliberate, because I used to use this to teach Java class loaders. So what the functionality is you take a Java file, and you drag it into the classes folder. And inside the class loader, it uses some of the tooling to actually run Java-C from inside the Java process. So it takes the .java file, it compiles it to a class file, and then it loads it into your system. So it cannot know anything about the class. That's the thing I'm trying to get across. You can't know anything about it. So let's have a look. We'll hit play. Okay, let's move that slightly. My clicking skills are off today. Okay, and I've set up this watcher. It's watching the file, and I've put some reflection code in here, of course, because it wouldn't be a Java demo without a little bit of reflection. So we do demo and class not found. Okay, so if you haven't seen one of those, there's your first one. I'm sure that's definitely been seen before. And what I'm going to do is I'm going to take this demo.java file, which is just effectively get a returns 42 and a setter, and I'm going to copy that into this classes folder here. Cannot paste selected elements. Okay, well, let's just try and drag it then. Cool. And if this has worked, which is looking like it might not do now. Oh, there we go. Yes, end of the day, laptop's slow, everything's running slow. I need a new Mac if anybody's watching wants to buy me one. And I've attempted to load demo.java. What is this thing? And then it's compiled it to a class file, and now the class is loaded. So if I go in here and type in demo, I can now see that I've got get a and set a. Now, I showed this as an example in a presentation, and somebody said, cool, so that means I can write Java code and put it into the JVM at runtime, and nobody will know anything about it from production controls. It's like, maybe want to step away from that slightly. And as you can see, it's really just created the .class file. So Java-C, it's not that smart. You can use it in lots of smart ways. But there's more to the story. And actually, the biggest part of the Java story starts after class loaders. Interpreting. So this is actually, if you were to go to a talk 20 years ago, maybe a bit longer, about Java, you'd probably be in one of the talks why Java is really slow. Okay, and this is where it kind of got its reputation for being quite slow, was that it was originally just an interpreted language. Lots of work has gone on in the background to sort of improve that performance, and we'll talk about some of those techniques as we go along. So initially, your bytecode, fully interpreted. Okay, and I'm going to say fully interpreted now because there's so many options to change that behavior. But in the default JIT compiled Java JVM, it's not, there's fully interpreted bytecode to start with. Now, you have this conversion of instructions to machine instructions, which uses a template interpreter. And there was a great talk by someone called Alex Blewett about HotSpot under the hood, which goes into a lot of detail if you're interested in how to take bytecode instructions and convert them into instructions on the fly. Now, the idea is that you don't spend time compiling code that you only use the one or two times. And think of traditional applications like Spring, where when you start up the application, it's doing lots of reflection, it's kind of trying to boot up your application. Like a lot of those methods maybe just used a handful of times. So there's maybe not any benefit to compiling them at the beginning. And we'll talk about the benefits you get from compiling everything up front versus at runtime as we get through this talk. There is kind of there's a trade-off. As with everything, there's no free lunch. Now, what interpreting allows us to do is it allows us to monitor the behavior of our application and make decisions on how we're going to compile and how we're going to apply some critical optimizations which are going to improve the performance of our Java code. Cool. That's where it gets interesting, because we've got this information, so what do we do with it? Well, there's a thing called the JIT compiler. So what the JIT compiler does, or C2 compiler, if we're going to be specific for the HotSpot example, it observes the code as it's been executing. And please don't confuse this with complicated profiling. So there's lots of profiling that exists. This is purely tracing through the invocations that you've done. It captures some various different counts, and then you trigger a compilation when you meet a threshold. So everything is done on a method-by-method level, and we'll kind of explore that through one of the examples that we'll look at. And essentially, you're trying to find the hot points in your application where you'll benefit from potentially bringing some of the bytecode together, eliminating some pieces for when you actually bring out your compiled instruction at the end. So utilizing that profile is really key. Like at the beginning, as we've just seen with that example, Java doesn't necessarily know anything about what you're trying to do. And that's intentional, because things that pull in from anywhere, it generally doesn't know. And we want to emit essentially our machine code instructions to replace the bytecode that we started up with. So applications running, bytecode is being interpreted, something's being used a lot, you take that to one side, you asynchronously dispatch it onto another thread and say, compile me this method. And it goes in the background, it compiles it, and when it's ready, it will do some pointer swiddling, and it will replace that in the running application. So at the moment, or at least kind of historically, our main option for JIT compilation has been the C2 compiler, okay, which is the second level of compilation. So we're talking about server mode compilation, and it's implemented in C++. Okay, so a lot of when we're talking about Java and it being slow, it's the main sort of the engine that's doing all the compilation historically has been written in C++. But there are challenges with C++. Now, got to kind of paint a little bit of a picture here, because we've got quite far with what we have. But what kind of things do we see when we try and build C++, maybe from 20 years ago as an example? Well, you've got this problem that it's unsafe. Okay, so if you've ever worked with C++ and you kind of go and you accidentally reference something, or you've removed something, you end up in a situation where you get a segmentation fault. Okay. I'm not going to say you don't get those in Java, because I certainly remember times that when you do. And actually, that's probably down to partly the unsafe nature of the language behind the scenes. And partly that's because there's a mixture of the pointers that are used in C++ and within the compiler and what we call an ordinary object pointer, or an OOP. And that's what's used to represent an object instance in C++ that's actually allocated in Java, essentially. So it means it's managed by the garbage collector. Okay, so if it's managed by the garbage collector and you then go and delete it, and then Java tries to delete it, things go really bad. Now, this dialect of C++ is also legacy. Now, this is, just for the recording, this isn't to say C++ is legacy, because I know Strauss quite well, and he'll probably tell me off for that. But what I mean by legacy is this dialect, it's very difficult to maintain, and it's not kind of like modern C++ 11, 14, 17. It's much sort of older than that. And there is actually custom memory allocation malloc processes that have been written in the background for the libraries. And again, the legacy kind of points to the OOP mixture of trying to take those two languages and put them together. Also, the tooling's a little bit tricky with C++, and especially this old dialect as well, and that kind of combines to make it difficult to make changes. So what we're actually saying is a story that happened 20 years ago when we started using Java in the first place. like a lot of these problems that we're talking about on the slide was, Java was always this blue-collar language to replace C++, or sort of help with those problems that weren't needing deterministic performance. Okay? And actually now we've got the similar problems inside the JVM itself. So the one thing to say is, though, it's been built upon over 20 years. It's a really awesome piece of engineering. But now there's a couple of other things. Like when we originally had Java and the JVM, it was all about Java. There are so many other dynamic languages that are running now on the JVM that it kind of changes the story a little bit. And some of the stuff that we want to be able to alter, it becomes very difficult. So the other side of this is that Java's now fast enough to be a compiler in its own right, which is also kind of cool. So how do we get this into the application? I mean, it's still this is great. We've got this got the C2 compiler, but what do we do here? And this is where this idea of the JVM Compiler Interface comes in. So the JVM Compiler Interface is a mechanism that allows you to replace the compiler within the JVM. All right. So this is kind of where we can now potentially use either the C++ one, or we can use something written in Java. Okay, so that's where we start to see a bit of a difference in the story that we wouldn't have had if I was presenting this 3 or 4 years ago. So what does the JVM Compiler Interface actually do? Well, it gives you access to VM structures, so that the compiler can see things like the fields, the methods, and that profile information that you've captured. And then it gives you a mechanism which you can use to install the code that you compile using the compiler. Now, it's kind of interesting because when you start to think about, well, what is a compiler? What does the interface actually look like? And fundamentally, it's a method that takes a byte stream and returns a byte stream. So its interface is kind of simple, but what it does behind the scenes is then fairly interesting. And what the idea is that you're producing machine code at the method level, and there's a use of JEP 261 as well, the modules, to kind of do some of the security and isolation parts, especially with the Graal implementation. So that kind of the security becomes an interesting point when you start saying, I'm going to just plug in some code and run it on Java. That's for obvious reasons. So what about Graal? Okay. So Graal is kind of an interesting, and again, like I say, we've been looking at Graal as a VM. What I'm going to show you is we're actually going to debug through some Graal compiler code, so you can see the part of Graal that we use here, which is basically Graal compiler, to generate effectively these machine code instructions. Now, it fundamentally, like in terms of how the JIT compilation is working, it's not doing anything super revolutionary, like the structure. You may have heard like the term sea of nodes, and the idea that you take effectively a graph that represents your program as it's running, and then you do optimizations to that graph essentially, and then you take the output graph and emit that into the actual machine code itself. So it uses a combination of what's actually going on, what does a profile look like? It runs through a series of phases, and then you end up with your output code, which is a lot quicker than being interpreted. Okay, now implementing a JIT in Java is actually a fairly compelling story. You've got language level safety and expressions, and it's pretty easy to debug, which I'm hopefully going to show you it's quite easy to debug, but we'll see how the demo goes. There's also really good tools and great IDE support, because ultimately it's using all of the Java stuff that you probably use for your day-to-day development. So how do you get started with this? Okay, so if you wanted to do, I'm going to write up a post on all of the different steps that you would have to take. But effectively, there's a command line tool for Graal called MX. Now, what the MX tool does is it effectively allows you to run builds of the Graal compiler in the example that I'm using. So I've pulled in the Graal VM project locally onto my laptop, and I'm working specifically, as I mentioned, within that Graal compiler sort of area. What you can do then is you can run mx build, which will build you the Graal compiler and give you effectively a jar file. And you can also use the IDE in it, and if you're going to do the debugging stuff, that just makes it super easy. And then what you can do is you can run mx-d VM. So what this is basically saying is I want to run a VM, and I want you to install effectively the Graal compiler that's local. So you'll actually see then it replace and put it in. I'm not going to run through all those steps in the demo because my laptop's old and it's not the fastest of things to get working. So I've got a bunch of options, of course. So I'm unlocking the experimental VM option. I'm going to enable the JVM compiler interface. and I'm going to use the JVM Compiler Interface as well. So that's going to give me essentially the JIT running in Graal. So if you were to run that on OpenJDK 13, you would be running the Graal compiler in the background, because that's all kind of like shipping with Java now. And actually, just to limit the scope of what we're doing, I'm going to say I only want to compile hello world and system error print line. Okay? And there's a reason for that, and I'm going to show you why that happens when we finish doing the debug. I'm also passing in a parameter to say dump out everything that Graal is doing, and that's for another tool that we'll look at too. So there is a tool that also ships, it's an Oracle Enterprise tool called Ideal Graph Visualizer, and this allows you to observe the compilation sea of nodes at the different phases that you go through. So we're going to explore something called inlining. Okay? And if you've not heard of inlining before, in C++ there's a keyword called inline, and it is kind of like up to the compiler whether it starts to pull things in together. The inlining keyword in Java, the inlining mechanism in Java is different to supplying a keyword, and it's different to the inline keyword as well. What it does is it allows you to explore the current execution chain and look at opportunities to bring those methods together. So if we think about what happens in our example, we call printint. That moves up the stack frame pointer. It has to have all the locals, the return addresses, and the parameters. And then when we call printline, it does the same again. So you end up invoking and expanding your stack frame. And then when you come back, you essentially collapse those away. So looking for opportunities to inline is one of the biggest performance wins that you can get in a Java application. And then effectively, you end up with the bytecode all chunked together, or the machine code that comes out of it all chunked together. So let's have a look and we'll step through some of this. Okay, so I'm going to fire up this debug example. It just has exactly the same output that's on the slides, just so I don't end up typing something completely wrong. And it's now waiting for my IDE to connect. So I'm just going to go over to IntelliJ. And into here, just so you know, the Graal compiler doesn't have lots of arbitrary system.out.print lines in. That's me adding things into here just to kind of like show as an example. So this is the first thing. So I've got a compilation request. So the JVM has gone, oh, there's something interesting here for you to compile. And we can see down at the bottom that that's the printint function. So the printint function is effectively the one that we're looking at. And if we look at our bigger display and output, that's effectively what's happening there. So we can start to have a look, and we'll just spend a couple of minutes exploring this just so you can get an idea of how you can go in and actually just debug the compiler. So we can step into the compile method. And what really happens then is there's a bunch of sort of startup that goes on. So we have a check to see if we're shutting down. We grab hold of the method. We kind of wrap up the task inside a compilation task. We do some setup and some debug, and then eventually we get down to actually running the compilation. So if we actually look at the thread monitoring on the left here, you can see that I'm in the JVMCI compiler thread. So this is separate to essentially the running application. So it will be paused obviously in the background while I'm doing this because it's just debug mode. But if you're running your application normally, other things would still be being interpreted even though you're asking for it to be compiled. So you can have a look in here. We grab hold of the runtime compiler, so we kind of can step through this a little bit. It has a look to see if this is on stack replacement. If it's on stack replacement, that means you're in a There we go. That's the best demo I've ever done. The sellotapes only last for like 3 days exactly. Cool. I think it's just the heat coming off my laptop probably has melted the tape at the back there. Okay, cool. So we go through here, and we're just effectively creating the wrapper for running this compilation. We'll just go into this next piece because we start to get to something a little bit more interesting. We'll skip over this part into the actual compiler. Okay, so this is where we start to see the first part of what I was talking about. So the first thing that happens is we create that graph. So the idea of the graph that's basically the bytecode and how it all connects together. So we grab hold of that. That's the first thing we do. It takes a little bit of a while to process that piece. We get a compilation result, and then we can go into the actual compilation here. So the thing that's interesting then is the actual the actual compilation phase. And I'm not going to go, we'll just look at inlining in detail and not kind of the pieces around it. But here you can see that there are the main things that actually get processed. So you've got this idea of suites, and the compilation suites are effectively the different phases that we're going to go through. So we've got this idea of high tier, mid tier, and low tier. And I'll show you a slide that will kind of expand out on what each of those things do. We have our profiling info. So that's the profile information that we mentioned that it needs in order to be actually do the compilation. And then we've got some options here as well. So you actually see that if we step through this, it effectively goes through and it applies all the different phases. So actually, if you were to go into your IDE and just type in phase, you'll see all the different phases that are there. So the one that I've kind of highlighted for us to look at is going to be the inlining phase. Now, the interesting thing here is that before we go to the inlining phase, there's two things that are happening. There's this idea of front-end compilation and back-end. So the front-end compilation is basically taking that sea of nodes, canonicalizing it, applying all the optimizations, and then you get the nice tree that's what you want to compile effectively. And then the back-end emitter is what then converts it into the target platform that you've got running. So for me, that would be the AMD Mac one, essentially. So if we go on, we'll see that we get into inlining data, and that's actually inside the inlining phase. So you can go and have a look at the phases and what they're doing. We can have a look through this and see what actually goes on. So we go into effectively looking and traversing through the different nodes that are available. So we ask if something was inlined as a bool to check, but the actual, it's kind of interesting, all of the behavior is within the actual data node itself, which is the inlining data, which is kind of nice and encapsulated and all those other good things that we wanted to see. So if we pop into here, we can have a look and we can see that it basically goes through and it captures what the current invocation is. And as we go through this function, we'll see that it asks if I should go into the next invoke. So what you end up doing is going through, having a look, and then you capture, well, I capture what the call site holder is, and then what the invoke target was as well. And if you've got some info as part of this, if you get inline info, then you can potentially look at doing the inlining. Okay? So what I'll do is I'll just press play here, just to allow it to go through, and we'll just have a quick look at the output. We're emitting the backend there, and it installs it into the code cache. That's just returning out. And then we're going to actually go and look at the hello main just very briefly. So what we can see here is that we step through each of the different phases. We looked at print line, we looked at print int, but we made a decision not to effectively inline at this stage. Okay? So that decision is kind of an interesting one because it's going to probably have more effect if we inline it directly into main, rather than trying to do some inlining here. Also, the other thing that's interesting is print line itself can't be inlined. So it's kind of going, well, I can't do anything at this stage. Now, one of the things that you're seeing here, you might be wondering, well, where's all the rest of the stuff? Because I've told the compiler to limit to just those two things, it's not actually going along the print line chain, which has a load of other buffers and other things that we could inline. I'll show you that in a second. So if we jump back over through this then, and we're just going to skip through the compilation pieces, we end up in a situation where we actually have something that we can inline. And it's essentially what you get is it goes through, it can do the inline, and then it will start to process that and output the effectively corresponding bytecode. So you get the decision then from the policy that it should inline. And then behind the scenes, it actually goes in, it canonicalizes the nodes, and then pulls effectively all of that graph, or all of that chain of methods together. I can't remember, I think I've left the last debug in, but if not, we'll return to the slides, which kind of shows you the machine code itself. Let's see if it's there. Okay, so this is where we're then emitting the back end, so we can have a look at whereabouts are we? Yeah, so you can see there we've got the AMD 64. That's a HotSpot backend, and we can, if we step through that, we should be able to see the compilation result. And inside here, you can see all things like the source mapping, the data section itself, which has got inside it all of the different pieces. So you can actually go in and you could go and look at all those things, and it's kind of quite nice. However, I should have started this by saying you probably won't want to do this that often, so you probably may just want to see what decisions the compiler has made behind the scenes. And what we'll have a look at is I have another script in here which does the example inline. which is kind of without, I've taken off the compilation limit. So it's going to go through and effectively run the whole thing. So if we do example inline and we pipe that into a less, then what we will see is that you actually have, maybe I'll just make that slightly smaller so it fits. You'll see that actually you start to invoke a lot more from, so you've got main, you've got print stream, and you can see that effectively that list going down. Now what's kind of interesting, if you run this with effectively no limits turned on, so I've not got any, I've turned off like, don't just compile this stuff, just go knock yourself out, you actually start to see something quite interesting. So you end up in a situation where all these kind of odd things start to get compiled. So you can see, I said, well, they're not really that odd because we were familiar with them in Java, but I certainly didn't have any hash maps in my application. Okay, so what's going on there? And actually, if I go have a look and see if there is any hello world, there's nothing. It still might decide to inline things, but that's for something else. So the reason why this is happening, and the reason why you see all this, is because Graal is actually compiling itself. So one of the things that you sometimes see when you're using Graal as a compiler, as a JIT compiler, because it's in Java, obviously it's interpreted. And if it's interpreted, you need to compile it to make it quicker. So what does it compile it? Well, it compiles itself. So you end up with this kind of slowdown at the beginning while the compiler is compiling itself. And actually, it never got to compiling hello world for me because it ran out of time and the program had finished interpreting. So just to kind of not keep you hanging around, I actually have this one where I just increased the thing to 10 million. So when you go to 10 million and you go and have a look, then eventually we do actually get our hello world, and you start to see all of the different pieces getting pulled in. So you've got things like actually string concat helper, string size, mix length. You've got the probabilities. All of those get folded in. So that's kind of cool, but you do pay this cost of having to start up because it's Java, right? It's slow, at least when it's not compiled. And that's the key with Graal. With Graal as a compiler, sorry. And there are going to be some tricks that we can look at that kind of maybe make that trade-off a little bit easier for you. OK, so the debug went quite well. We lost a sign for QCon at the front, but generally we're getting there, and it's T minus 20 minutes to beer, so that's always a good thing. So what do these phases look like? Well, I mentioned we have this high tier, mid tier, and low tier. You can actually go and step into those. We're going to focus on the high tier. One of the things that I'm planning to write is an exploration in more detail into each of these phases and actually stepping through some of the graphs that you can see. I will show you the graph that came out of the application when we go back out of this. So we've kind of looked at inlining. There's a couple of other optimizations that are worth knowing about, and we'll explore those now. One thing that's interesting is you'll see that you have a lot of canonicalization phases that happen just to kind of rebalance the tree into a format that is known before it kind of goes through the phases. And you'll also see dead code elimination starts to feature twice. And dead code elimination is really interesting. So what dead code elimination does is not kind of like when you've written something in Java and it goes, you can just delete that because you did something stupid. It's a lot more around the idea that, well, at runtime, you maybe never need that branch of code, right? And if you were to compile that, or you may never use that method is another example. And if you were to compile that, it would potentially make your application, or your compiled part of your application much bigger than it needs to be. Now, Alex did a great talk yesterday about low-level optimizations at CPU. And what you can sometimes get by pushing in a new function that you didn't know about is you can change the way in which your application profiles. So it's kind of nice that what you see in Java is that anything you're not using, anything that's irrelevant, any kind of branches that you don't need will be removed. And that removing of branches, it decreases branch prediction, all these other things. So it actually ends up having a really good effect on your overall application. And you could do this twice, once at the beginning and then once when you've kind of done some of the other factors later. So again, this is determined at runtime. It's determined by that profiling information. And that's why that profiling information is so key. Another one is unrolling loops. So loops themselves, they require back branching and branch prediction, as well as the actual overhead of doing the counting and everything else. So what if you could unroll those and kind of make your application simpler? So when you use an int and you iterate over a for loop, you can actually take that for loop, and when you compile it, you can remove all of the iteration and just lay the code out effectively linearly. So you end up with like all of the instructions just together. And that kind of then removes a lot of the different kind of like having to back branch, having to your application or CPU and prediction having to work really hard. The other thing it can remove is safe point checks. So safe point checks are triggered within the JVM when it's looking to do things like GC, for instance. And it will always do that when your application's in this sort of safe state. So the safe points also have a big overhead. And if you can remove those, that's a good thing. So there's a little benchmark here. This is straight out of Optimizing Java, where if you are running an int through the same code, basically it's the same thing, but it's using an int and a long, you end up with a throughput of 2,400 operations per second, whereas if you're using a long, that kind of drops off to 1469. So you kind of lose a lot of performance there just by how you create your loops. I was talking to a guy called Chris Newland about loop unrolling. I'm not really sure. I mean, I see the benefit with the benchmark, but how complicated can it get? And he was saying that he'd actually seen a double nested for loop that was doing ray tracing that had actually been loop unrolled. So there can be some really kind of heavy things that it gets down to doing. Now, escape analysis is a really interesting one as well. So escape analysis itself was introduced in versions of Java 6, so it's been around for a little while now, and it analyzes code to check if an object ever leaves the scope of the method or is stored within some global variable. Now, the nice thing about escape analysis is it kind of goes back to that age-old interview question of, in Java, where do you allocate an object? And obviously, you could just say heap, and you're probably about 80% right. But now there's so much more of a story to that. What escape analysis does, if the object is small enough, is it'll actually stack allocate that object. So going back to like the C++ style of automatic memory management, once the stack frame goes away, the object goes away. Now that sounds, well, why would you want to do that? Well, one of the biggest subsystems in the JVM is GC. And if GC is under pressure, as it often is by lots of objects that are created and actually lose reference and die quite quickly, you end up having to do more GC cycles. So if you can stop putting the objects there, you can potentially prevent the GC cycles. And obviously going on from that interview question now, you can talk about Valhalla and other things as well, because that makes the conversation even more interesting if you're in an interview. So it's kind of, again, it's a nice optimization that most people just got for free. And one of the things that I've certainly taken away from this conference is the more you're on the latest version of Java, the more performance benefits you're getting essentially for free. Now, the other one that's kind of inherent in Java, and if you worked in C++, you'll have seen this idea as well, is this idea of when you call a function in Java, the function is always virtual. And what I mean by that is because it's an OO language, it has to look up where the corresponding implementation is. And this is because Java is an OO language by default. Object is always at the root. You always have to kind of look up to see where the function you want to invoke lives. Now, if in C++, by the way, you can do static binding, which means it's there, and it just calls the function at the memory address directly. There isn't this intermediate lookup. Now, HotSpot, because we do that all the time in Java, it realized, well, one thing we want to do is optimize that away. If you don't want levels of indirection, that's, where as soon as you're indirecting a pointer, you're losing like locality. It's kind of difficult to do things with. So what HotSpot does is it's able to look at the vtable structure, which is a data structure which does effectively pointing to implementations. And once it's done it the first time, it can actually collapse that to be a direct call. So it can just go, it's over there because I can infer that from the way your application is running. Now, it's kind of interesting, again, because it requires the idea of tracing, and sometimes it gets this wrong. So class loading and the magical features of class loading mean that you can end up in a situation where that's an optimistic optimization, essentially. But what the JVM can also do, which I kind of like about the JVM, is if it realizes that it's done something that's no longer a decent optimization, it can revert back to interpreting and recompile within your application itself. So there is kind of like, it has a back out if it's not sure. Now, the other thing that you can also do is bimorphic dispatch. So if there are effectively two call sites, it's able to do that. Once you get to megamorphic, things start to, you lose optimization there. There's diminishing returns as you go through. People have worked on trying out trimorphic as well. And there's a great blog post I tweeted yesterday that goes into this in a lot of detail. So what happens then is your emitted code, effectively your machine code, it gets output into the code cache, right? And then what happens as you're running through is it replaces the interpreted running application. And as I mentioned, the other thing that's kind of key here is there's also this idea of on-stack replacement. So if you're interpreting, and if you think about it, most Java applications are running in some form of loop, because otherwise it would just stop. So the idea is that if your main function is busy, like it is in Hello World there, then you want to be able to replace the main interpreted loop with a compiled one. And that's where on-stack replacement comes in to actually be able to replace the code that's being interpreted with the compiled target. So that's all really cool, right? That's all nice. There's a bit of a bigger story that's starting to emerge as well. AOT, so ahead of time compilation. So what I've been telling you here is it's really great to do JIT. Because when we do JIT, we have all the information about how our application is working and what it's doing, okay? But it comes at a cost. You've got slow startup time, okay? Or you actually often have a spike of memory usage at the beginning of your application while you're creating all those temporaries to wire up Spring or whatever else. So that slow startup time and that high peaking memory, if you're running on something like cloud, it might not be the factor that you want to actually optimize for. And this is where you start to get into a trade-off of saying, well, JIT's really cool if for long-running applications, but it has slow startup. And actually, AOT is pretty good in cases where my application runs in almost like in a consistent way. So what could we do here? Well, we can actually use ahead-of-time compilation as well. So we can use AOT plus JIT, okay? So we've seen in some of the talks about Graal VM how you can supply a profile of your application. You can do effectively try and do some better optimizations there. Inside the JVM itself, there is a tool called JAOTC, so the Java ahead of time compiler. It was not designed to be said in a presentation. I think that's deliberate. And it's used to generate the target code for either a class or a module. Okay, so we'll talk about that in a second. The idea is that the JVM itself, it treats the AOT as being an extension to the code cache. So what you can do is you can stuff in pre-compiled either classes or pre-compiled modules into the JVM and still benefit from JIT. Okay, so there's a couple of different things that you could potentially do there. Now, someone asked a great question when I gave this presentation in New York. Like, what about if somebody tries to give you something that's not it doesn't work. Like maybe it's some random code, or maybe it just wasn't compiled in the same way. And the way in which you compile AOT code is quite specific. And what it does is it actually has like a fingerprinting technique, which looks at the fingerprint on the class essentially, and it looks at the one that you've got currently that's running, and it compares them. And if they're different, it won't be able to use that effectively at runtime, and it will reject it and go back to interpreted. So the JAOTC tool, it takes a class file and it gives you effectively a shared object. So like in this example. So in this example, I'm just doing a very simple hello world. I'm outputting it to libhelloworld.so, and then I have to use experimental VM options, AOT library, pass it the AOT library, and say hello world. Okay? Now, this slide makes it look really cool, and that works fine. But when you compile these things, you usually have to indicate what VM you're using, what GC you're using. That's one option. And you have to supplement it with other types of flags that you have as well at runtime. So there becomes a really big potential inconsistency between what you compile and what you run. So obviously the first thing we go is, well, that sounds like Java C. Where's my build tool? And actually, build tool support for this, it's not there yet. Okay, so if you wanted to do a mixture of saying, I'd like to compile this module but run the JVM as you normally would, there's no Maven plugin that does that. So something that I'm experimenting with at the moment, I mentioned, kind of comes back to the beginning of the talk where one of the things that I like to do is hack around on Apache Maven. So I'm actually working on a plugin at the moment for JAOTC that will enable you to kind of do that consistent rebuild and run with shared objects and mix it in with that kind of ahead of time and sort of JIT compilation as well. So there's always a trade-off. Like obviously these things, you kind of have to balance them out. And you'll probably have to try and find a balance between what makes sense to be ahead of time compiled. Maybe it's the stuff that you use at startup versus what you want to kind of leave to be essentially JITted. Okay, so the bigger picture. So we talked a lot about the JVM, how it works, how it gets interpreted, and everything else. Garbage collection is something we haven't really talked about much in this talk, other than there is garbage collection, you need to think about it. Now, when it comes to actually looking to see if your application is performant, a lot of the reasons why I give this talk is purely out of compiler interest and just because I like fiddling around and showing what's going on inside the JVM. If you have a performance issue, please don't start there. There are other places that your time would be better served looking into. So looking at like the overall profile of your application, almost most of the problems that you have with performance are going to be network, database, IO-based related. So look at those first. And then the other thing is like, well, what are you deploying on? And obviously cloud starts to complicate that story a little bit. So just before we go into the acknowledgements, I'll just show you the IGV tool just so you can see it. You can actually see a bunch of stuff that it was throwing out there as we were going through. So you can actually have a look at what like the high tier tree looks like after it's done and then what it kind of simplifies down to. Say simplify, still pretty complicated. Probably looking at print int makes a little bit more sense because it's a little bit smaller. So yeah, I'll send the link out to this because it's probably better. Yeah, you can play around with it and debug it and have a look yourselves. So before we go on to any questions, a couple of acknowledgements. Chris Seaton had a really excellent write-up about Graal as a JIT. Some of the stuff on there has aged a little bit, and that's the purpose of the blog post that I'm going to write. So if you wanted to pick this up, that will probably be the best place to start. I thank Ben Evans for teaching me a lot of this stuff and being patient with me when I didn't know anything. And Anna did a lot of the graphics on here. Martin for sort of running the track and Alex for running the track as well. The Graal VM and OpenJDK teams, like this is pretty awesome technology, like just in general. Alex Blake, thanks for reviewing all of my slides and hopefully picking out any of the errors that I did. And we ran this in the New York Java user group last week as well to give it a trial run. Cool. So thanks for listening. Hope you have a great evening.
So we've got about 5 minutes for questions if anyone has anything that they want to ask Jim.
Is there any work on taking the code cache from an existing running JVM and then using it as a ahead-of-time compiler?
Yeah, so certainly from what we've heard, I guess in different talks as well, like specifically with the like Graal VM, you could supply a profile to the ahead of time compiler, so it can kind of make some better decisions about the compilation that it does. There's also within, I think, some of the other JVMs as well, like there's an ability to effectively dump the profiling information that you get from the running VM, and you can supply that into some of the different tools. I haven't experimented on that with JAOTC yet, but I'm pretty sure there is support for that across a lot of the tool chains. So I know, for example, OpenJ9 does it, which is another JVM.
Okay, anyone else have a question?
Just to the front here, Alex. Thanks.
I have two questions, actually. So it seems that Oracle now essentially has two different JVMs, or two different JIT compilers. How do they compare feature-wise in terms of optimizations they can do, maybe performance-wise, in steady state, obviously?
Okay, that's a good question. So, so certainly the JVM as an ecosystem, at least within the scope of this talk, is the same. The difference is the pluggable JIT compiler. So you've got an option of HotSpot or you've got an option of Graal. One of the things that you sort of see again with HotSpot, because it's kind of in C++, it doesn't need to recompile. You will probably see faster startup times from HotSpot. With Graal, the things that start to become quite interesting is more of the dynamic languages that run on the JVM that don't necessarily have like techniques around boxing. So things like that, where previously you would have been slow, you could potentially get better benefits from being able to write phases that are custom to that particular language for it. For example, I'm going to air quote where I've heard this from because I can't remember exactly where it was, but some Scala sort of applications running on the JVM have seen like in the order of 30 to 40% improvements by using Graal. So, yeah, probably Twitter actually. Yeah.
Do you know if Oracle has any plans to kill one? Well, obviously, which one? Or probably HotSpot.
I would say they're supplementary technologies, but I don't work for Oracle, and I'm not 100%. I couldn't say what was in their plans. I reckon that Crystal Ball, they'll at least be around for the next couple of years, because I think the actual HotSpot project, it's the aim of this talk is to show some of the new experimental stuff. I think we have to bear in mind that a lot of the applications that we run are super fast as a result of HotSpot, and a lot of the stuff we talked about today is still under experimental mode.
Yeah. And the second question. Do you know what happened to ExcelSurJet?
What, sorry?
ExcelSurJet, they were developing ahead of time compiler, and they have stopped around the time that Graal has been announced.
I don't know, I'm afraid. Sorry.
Thank you.
Okay, I think we're out of time, which means it's beer o'clock. But before we do, please let's thank again Jim.
Thanks, guys.